Hello everyone, welcome back. My name is Mr. Kovalt, and in this video we're going to go over Le Chatelier's principle. We're going to apply Le Chatelier's principle to different situations and decide what effect it's going to have on the various species indicated. So let's get into this. Okay, so here it says consider the endothermic reaction, and here they give us the equation CaCO3, calcium carbonate, solid, in equilibrium with calcium oxide solid, CaO, and then carbon dioxide gas. Now, the first thing I want to do is it says consider the endothermic reaction. So endothermic means that the reaction is going to be absorbing heat. So if it's absorbing heat, it's got to be absorbing heat from somewhere, and we can treat heat as a reactant. If heat was being produced, that would be an exothermic reaction, so we could then treat heat as a product. But here, since it's an endothermic reaction, heat is going to be on the reactant side. So we can go ahead and add heat here, like this. And so therefore, that'll remind us that heat is acting as a reactant. So that'll help us when we're talking about temperature changes. Okay, let's continue. It says fill in the table below showing how the indicated change to the equilibrium system will affect the indicated quantity when a new equilibrium state is established. And so here we have this table. And so here are the changes that we're going to be making to the system. Here's the quantity that we're going to be focusing on to see how this change affects this quantity. And we're going to fill in the table what that effect is and why. Okay, so let's start with add CaOS, so solid calcium oxide. So you'll notice that calcium oxide is a product. So you might think, oh, look, so according to Le Chatelier's principle, whatever you do to the system is going to undo it or try to relieve that stress that you added, right? So if I'm going to add CaO and that's a product, you might think, oh, well, that means it's going to shift in this direction to get rid of the product, kind of lower that product because I added some, so it wants to lower it and create more reactant. And that would be okay. However, you have to pay attention to the state of matter. We should know that if it's a solid or a liquid, adding or subtracting a solid or a liquid from the equilibrium system will have no effect on the equilibrium system because the equilibrium system is only going to be affected by a change in concentration or temperature. But in this case, the concentration of a solid or a liquid doesn't really change by adding or removing some of it, right? So we don't like talking about concentration doesn't really make a whole lot of sense. So adding calcium oxide is not going to have an effect. So it's not going to have an effect on anything, but the quantity CO2 is the one that's mentioned. But again, it's not going to have any effect on equilibrium. So we're going to write no effect because it's a solid. Solid is not going to have any effect. Liquids aren't going to have any effect. So let's go to the next one. So here we're going to decrease container volume. So when you're talking about changing the volume of a container, you have to keep in mind the relationship between volume and pressure. And so if you remember Boyle's law, if you increase the volume, then you decrease the pressure. So volume and pressure are inversely related to each other. So in this case, we're decreasing the volume. Therefore, pressure is going to increase. So we're increasing the pressure. That is the change we're making, right? So we decrease the volume of the container. That's going to increase pressure. And so according to Le Chatelier's principle, the equilibrium system is going to adjust to relieve that stress. And the stress here is an increase in pressure. So how is it going to get rid of pressure? You have to look at which side has more moles of gas, not solid or liquid, just gas. And it's going to shift in the direction either to lower or increase the number of moles of gas. So, but if we understand or remember the relationship between pressure and moles of gas, the more moles of gas you have, the higher the pressure. So if you increase the pressure by decreasing volume, the system is going to want to decrease that pressure. So it's going to shift to the side that has less gas, less moles of gas. And so you can see here that the only gas is on the product side. So it's going to shift in the direction away from the gas. So it's going to take some of this and it's going to form some of this. So in that process, the question is, what happens to the quantity of calcium oxide? Well, calcium oxide is a product. If it's going to shift, if the equilibrium is going to shift in this direction, then that means it's going to use up some of the calcium oxide to form more calcium carbonate. So we would expect a decrease in the amount of calcium oxide. So this is going to shift. It's going to shift to the left. And we're expecting a decrease in the amount of calcium oxide during that shift. Okay. Next, again, we have decrease in container volume, and we're looking at the total pressure. What's going to happen to the total pressure of the system? Well, again, as we said, if you decrease the volume of the container, then the pressure in the container is going to go up. Le Chatelier's principle says that the system is going to shift in such a way as to relieve that stress. In this case, the stress again is the increase in pressure. Well, it's going to shift to decrease that pressure. So we would say, oh, it's going to shift away from the gas. So the only side that has gas again is this side. So it's going to shift in this direction in order to use up some of the gas here to react and reform calcium carbonate. So, but then the question is, what is the total pressure going to be? How is that going to affect the total pressure? Well, we said that initially you're going to decrease the volume, therefore increase pressure. So initially the total pressure will increase because of the change in volume, but Le Chatelier's principle is going to decrease that total pressure. So when you reach that new equilibrium state, the question is, will the total pressure be the way it was before? And the answer is no, because the shift can't ever go back exactly where it was before. So there's going to be some pressure still there from what you've added. So it'll decrease the pressure from where it was when you made the change in the volume, but it's going to go down, but it's not going to go down to its original state, so it's going to have some more pressure. So here, again, it's going to shift left, but in this case, the total pressure will increase. It'll be a little bit higher than where it started before you made the change, okay? All right, so next we have adding CO2. So again, according to Le Chatelier's principle, if you add a product or a reactant, it's going the equilibrium is going to shift in order to get rid of that whatever you added, product or reactant. So here we're adding CO2. So CO2 is a product. So the system is going to shift to get rid of that product, to get rid as much as it can to reach equilibrium again. And so again, I'm adding product So it's going to shift in this direction in order to use up some of that product to get back to equilibrium. So it's going to use up the CO2 and it's going to create more CaCO3. And so in that case, our focus here is the quantity Kp. This is our equilibrium constant, and as the name suggests, equilibrium constants are constant. So what's going to happen is you are going to change the concentration of CO2 initially by adding CO2 to it, but because equilibrium wants to go back to where it was, this carbon dioxide is going to react with the calcium oxide to reform some more calcium carbonate. So this is going to go down, this is going to go up until you get that ratio again. So remember, Kp, simply put, is going to be concentration of product over concentration of reactants. So you've got this ratio here. Kp is equal to this ratio. Well, nothing affects that ratio. Adding CO2 or maybe something else, right? Adding a gas is not going to change the equilibrium constant. The fluctuation or the adjustment by the system to get back to the equilibrium is basically getting back to this ratio, which is Kp. So adding CO2 is not going to have an effect on the equilibrium constant. So this is going to be no effect. So we'll talk about it'll shift left again, right? That's going to be the shift, but it's not going to have an effect on Kp. No effect on Kp. Okay, next we're back to adding CO2. Same thing here. So again, we're adding CO2. It's going to shift away from the CO2 in order to use up some of that CO2 that was added to get back to equilibrium. But if it's shifting in this direction, we're looking at what's going to happen to the CaCO3, the calcium carbonate. And the answer is that it's going to shift it to the left, and it's going to increase the amount of calcium carbonate you have. So that is the answer here. So it's going to shift left again, and it's going to increase the amount of calcium carbonate at equilibrium. Okay, what about adding helium gas? Well, helium is a noble gas. It's inert. It doesn't react, and you're adding it to a system that does not use it. Helium is not involved in the reaction, so therefore, adding helium gas is not going to have any effect on equilibrium. There's going to be no shift. So this will be no shift on the equilibrium, therefore no effect on the amount of CO2 at equilibrium. Okay, now what about increasing temperature? This is where you have to be careful because increasing temperature does change the equilibrium constant K. So you got to be careful with this one. So here we have increased temperature, and we want to know what's going to happen to CO2. This is where knowing whether or not the reaction is endothermic or exothermic is going to be helpful. So in this case, we have an endothermic reaction, and as I said at the beginning of the video, that heat can be treated as a reactant. So when you change the temperature, you can think of that as either adding or removing heat. So if I increase temperature, well, how do you increase temperature of something? Well, you put heat in, you increase the heat, right? So you add heat. If I want to decrease temperature, well, what do? Well, I subtract the heat, right? I remove heat, right? So I'm either adding or removing heat in order to raise or lower the temperature, right? So if I think of it in those terms and I think of heat as a reactant, then I go back to the same idea of adding CO2 or removing CO2 like that. So here, if I'm increasing the temperature, I am adding heat in order to increase the temperature. Well, what is going to happen? Well, if I'm increasing heat and heat behaves like a reactant, well, it's going to shift in the direction away from the heat in order to use up some of that heat that was added. And it's going to use up some of the calcium carbonate, and it's going to form some of the calcium oxide and the carbon dioxide. So in this case, the CO2 is going to increase because the shift is towards the CO2. So it's going to shift right. And it's going, therefore, it's going to increase the amount of CO2. And finally, the last one, increased temperature again. What effect is it going to have on the equilibrium constant? And in this case, it is going to have an effect on the equilibrium constant. So again, the same idea here. It's going to shift right. And we want to know what's going to happen to the Kp. Well, in this case, you're not changing any of the concentrations in changing the temperature. Let me rephrase that. You are going to be changing the concentrations, but you're not changing the concentrations directly. It's not like I'm changing the concentration when I add, like I do when I add CO2. So when I add CO2, I am changing the concentrations, but the system will equilibrate again in order to adjust those concentrations in order to get K, that ratio. However, I'm not adding anything or removing anything that is in the K, the K constant expression here, right? I'm not adding product. I'm not adding or subtracting CO2. I'm not doing anything here, and if I did, it wouldn't matter anyway because they're solids, right? So I'm not changing, I'm not, how do I say? I'm not disrupting the equilibrium by changing concentrations or amounts of gases or things like that. All I'm doing is changing temperature, and then it's going to adjust in order to get back to equilibrium, and the system itself will change whatever the concentrations were, and the Kp depends on those concentrations. So changing the temperature will change your equilibrium constant, right? So, but how is it going to change it in this case? Well, if I, again, think of heat as a reactant and I'm increasing temperature, that means I'm adding heat, and therefore it's going to shift this way again. So it's going to shift to favor more product formation, right? So it's going to shift right, and then if I remember here, the K value is only going to be dependent on the amount of CO2. Remember, the solids and liquids do not show up in your expression for K, so your Kp for this reaction is going to be equal to, again, concentration of products over reactants. This reactant is a solid, this product is a solid, so they're not going to be in the expression. So the only thing that's in the expression is the partial pressure of CO2. So the constant, the equilibrium constant, is directly related to the partial pressure of CO2. So therefore, if this is going to shift in this direction because I'm increasing temperature, right, then I'm going to increase the CO2, and if I increase the pressure of CO2, then I'm increasing Kp, so that increases. So the Kp value, the equilibrium constant at the new temperature will be higher than it was before. And so, and again, if I didn't mention it, I think I mentioned it, but I'll mention it again. The only thing that will change the K value, your equilibrium constant, is a change in temperature. Because your equilibrium constant depends on temperature, and therefore changing the temperature is going to change the constant. So that's why when you are doing a problem where involving equilibrium, and they give you the K value for that reaction, they usually tell you what temperature it is at, so that you know that K value is related to that temperature. If you change the temperature, then that K value is no longer going to be useful for the reaction at that new temperature. So I hope this was helpful. If this was helpful, if you learned a lot, and you found this interesting, then please by all means like the video, share the video, hit that like button. Also subscribe to my channel, hit that notification bell up there. When you do that, click all so be notified by all the videos I put out. And finally, put a comment down below in the comments section. Let me know what you think, ask me questions. I would love to hear from you. Thanks for joining me, and have a great day.